This is section 6.3, theory-based approach for two proportions. As always, make sure you actually pause the video and read these learning objectives. It is important to know what you're trying to learn in the section. I just don't read them to you because you can read those by yourself. Okay. So let's start with our theory-based method. If our sample size is large enough, we can approximate what the null distribution of the possible differences in the proportions. We can take that null distribution of all the possible differences in the proportions and we can approximate that with a normal distribution. Okay. And to do this, though, we need to make sure we have a big enough sample size for the central limit theorem to actually work. So the validity condition is we need at least 10 successes and at least 10 failures in each sample or each group, depending on how you want to think about it. Okay. So just like when we did one proportions, we need at least 10 successes and 10 failures, but now you need it in each sample or each group. So confidence intervals, our general formula has always been our statistic plus or minus some multiplier times the standard error of the statistic. And this multiplier comes from the normal distribution, which is why we need to make sure that our sample size is big enough to actually use this multiplier. So our statistic in our case is this p hat 1, the first sample proportion, minus the second sample proportion. That's our statistic for this chapter. Plus or minus d star, that's your multiplier, and then times it by the standard error of whatever the standard error of that difference in your proportions. Now your standardized statistic, our formula has always been statistic minus mean of the null distribution over SD of the null distribution. So in our case, our statistic is this difference in the sample proportions, p hat 1 minus p hat 2, minus, now the mean of the null is always going to be 0 because we're always comparing our two population proportions, so you can just automatically put a 0 there. And divide by, so it's supposed to be standard deviation in the null distribution, but we're going to use the standard error of our difference in proportions. The reason why is the formula for the SD of the null distribution requires knowing the population proportions, and we don't know those, so we can't actually find it. But we can estimate it using the sample proportions, and once we do that, we call it standard error. And just as a note, when you're checking the validity conditions, you don't look at the totals, just the actual successes and failures. So, for example, remember our blood donation example. We want to conduct a theory-based significance test to determine if the percentage of people that donate blood changed from 2004 to 2014. So it didn't say increase, decrease, it just said changed. So this is going to be a not equal to hypothesis. But first, let's figure out, is the theory-based approach valid here? So we need to check at least 10 successes and at least 10 failures in each group. When we look at that, we don't look at the totals. We only look at these numbers right here. So check if these are at least 10. Okay. In this case, they are all at least 10. So yes, we can use the theory-based approach. Now there's two ways we can put this into our applets. Okay. We can use the two proportion applet. Let's pull that up and I'll put the data in. So once you have your two proportion applet pulled up, you put in all your data. Remember, for the applet to work, you do have to put the explanatory variables, the groups that you're comparing, along the columns. Click Use Table, and make sure that the thing you're interested in, whether or not they donate, the donate is what you're looking at, and we're doing 2004 minus 2014. We could have switched that, but that's just the order I'm going to do. Click Show Table. This will show you your table here. It will show you your observed difference in proportions. Click Show Shuffle Options. Now you can actually shuffle if you want, okay? Or you can even skip the shuffle and you have to click Overlay Normal Distribution. Okay? But you didn't say what was your observed difference in proportions. It was this 0.05, so I put 0.05. And we said that we need to do a not equal to hypothesis, so we're going to click Beyond and count. And it will tell you what your p-value is and your standardized statistic right here. I do like, though, to go ahead and ask it to shuffle. This is a very big data set, so I'm only going to do 1,000 or it would take a really long time. But now you can see the normal curve overlaid. You can see it follows it pretty well. I mean, not exactly, but pretty well. And again, this is your theory-based p-value, your theory-based standardized statistic. Let's come back to our notes. I realized while we were here, I didn't write, so I like to say, okay, 2004, 2014, that was my explanatory variable, and over here I had my response variable. Just get in the habit of checking that because on the test they could maybe switch which variables they put where. Okay. And I realized I didn't ask you to find the hypotheses. We should probably do that, right? So the null hypothesis would be that my population proportions are equal, or if I subtract them, I should get 0. And the alternative hypothesis is not equal to 0 because we just said we want to see if it changed. We didn't say which way we think it'll change. So now let's make a few notes on here. Make sure you have to do this overlay normal distribution to get your theory-based p-value and test statistic. And you have to do beyond because it was that not equal to alternative hypothesis. I just put in my sample proportion there, or my sample difference in proportions. And notice if I click the box for the 95% confidence intervals, this will be my theory-based confidence interval. So you can do everything in this two proportion applet if you want. You can also use your theory-based inference. So when we go to our theory-based inference calculator, you have to click on two proportions. And I actually find that this one's faster if I'm not given the entire table because I don't have to figure out how many actual failures there were. Okay. But you'll type it in, you say, okay, what was the sample size in the first group? The first group had a total sample size of 1336. The other group had a sample size of 1315. And then you put in the count of how many people did what you wanted, in this case, which is 230 for the first group and 161 for the next group. It will calculate the sample proportions for you. Then you click on test of significance. I want it just equal to 0. I'm going to put a not equal to because we decided it should be a not equal to. And it will give you your standardized statistic. It will give you your p-value, and you can also click confidence interval if you want 95% or if you want some other level. And there's your confidence interval. So either way, doesn't matter which applet you use. Okay, we can look at the applets to find our standardized statistics. You'll notice that we're a little bit off. That's just due to the rounding from different applets. They coded them slightly differently, but you should be fairly close. So we'll say our standardized statistic is 3.61. And to interpret it, it's always how many standard deviations are above the mean, but in this case, our mean is always 0. So sometimes we like to say our difference in proportions, our statistic, was 3.61 standard deviations above 0. Okay, that is surprising. Okay, anything above 2 is surprising, so this would tell me right away that I have evidence against the null because z is greater than 2. Well, now what is our p-value and interpret? So we just come back up and look here. My p-value is 0.0003, or here you can see your p-value right there, 0.003. Notice it did line up exactly with my simulated approach. That's just a coincidence. Usually they're not exactly the same. So my p-value is 0.0003. And how would I interpret that? I would say something like there is only 0.03%. We like to change the percents just because it makes more sense to people. 0.03% chance that we would get our sample data or our sample difference in proportions of what was our difference? 0.05, 0.05, or beyond, or more extreme, if the null is true, or meaning like if the blood donation rates had not changed. Now I'm realizing I forgot to tell you a few things, like I didn't have you write your hypothesis and I didn't ask you for the conclusion because we'd already practiced those lots of times. So I would say that is a small p-value. So the null is not plausible. So the null is not plausible. So we have evidence that the blood donation rates have changed. Now, I'm not going to say whether it increased or decreased because that wasn't my hypothesis. That's not what I was looking for. I just asked you to tell me if they've changed, and yes, they have changed. Now, I might ask you, what is the 95% confidence interval, and interpret it. So these are theory-based intervals. You can see it here on the theory-based applet, or you can see it here on the simulation applet. It will always give you the theory-based confidence interval if you click that box. They just round differently. So it is 0.0228 to 0.0766. So to interpret it, we can say something like, we are 95% confident that blood donation rates were 0.0228 to 0.0766 higher in 2004. So I know it was higher in 2004 because 2004 was the one that I had first, and those were positive. You could also just like look at your bar graphs and say, oh yeah, 2014 was higher. Or up here like 2004 was higher. That first group was higher. So that one actually does tell you like, okay, which one was higher, how much was it higher by. Confidence intervals give us a lot more information than p-values. P-values tell us how strong our evidence was, but the confidence interval will tell you, okay, you know it changed, this is how much it changed by, and that can be even more useful. If you want to know the 90% confidence interval, we would come to our ISI applets, our theory-based applet. We would put in 90% for the confidence interval, and it tells me that's 0.0271 to 0.0723. And if you want 99%, you come back and you just change it to 99%. So I get 0.0144 to 0.0851. So as you'll notice, if we go from 90% to 95% to 99%, as we increase our confidence level, the confidence interval gets wider, which we've talked about before. The only way to be more confident is to just make your interval wider. The reason it gets wider is that multiplier gets bigger and bigger, so our confidence interval gets wider. Now, remember our polio example that we looked at before, where they gave people the vaccine or the placebo, and then they kept track of what polio rates, if they got polio or not. So in our case, whether or not you get the vaccine or placebo, that is actually your explanatory variable. And polio or no polio is your response variable. So this table is switched. Okay, and I told you they can give it to you with a switch because there's no rule of how you want to do it. But this would be an issue if we wanted to put it into the applet. Okay, because our simulation applet, you have to have it arranged with the explanatory variable along your columns. Okay. But it turns out these sample sizes are actually too big for the two proportions applet. So we're just going to use the theory-based applet anyways, so we don't have to rearrange it. You just have to be careful in your mind. If you wanted to rearrange it, you could just rewrite your table and change it, and you could say, okay, let's put your vaccine here, and your placebo, and polio, and no polio. And you could just quickly do that on your own paper. You're like, okay, vaccine and polio is like 56, placebo and polio is 142, etc. And you could just rearrange it yourself so you could put it into the applet. But we're just going to use the theory-based applet. But I have to look at it very carefully. So when I want to find like my statistic, let's start by doing it by hand, then we'll put it into the applet. I need to look at the sample proportion with the vaccine minus the sample proportion for the control. Now, you might choose to put that in a different order. That would be okay. This is just the order I picked. We have to put the treatment first just because it was what we cared about, but you don't have to. So when I want the sample proportion for the vaccine, I have to say how many people got polio with the vaccine, which was 56, and how many people were there total that had the vaccine. So it's out of 200,000. So it's kind of hard to switch your mind to do the rows when you get so used to doing columns. So it might be easier for you just to rewrite the entire table. And then for control or placebo, there were 142 people with the placebo that got polio out of a total of 200,000 people that had the placebo. If you put this into your calculator, you 0.0004. the parameter that we're interested in. So we know our statistic, but we don't know our population proportion, our pi. So what's the difference in the actual population proportions? That's what we want to figure out. So we know the difference in our sample proportions. We want to figure out the difference in our population proportions. What are the actual two populations? Well, it's all people that get the vaccine and all people that get the placebo. Those are the two populations that we're interested in. So are the validity conditions met? What numbers do you actually have to check? Only check the actual successes and failures. They are all at least 10. So yes. Okay. The null hypothesis would be that the vaccine doesn't work. Okay, or that the population proportions are the same. So the population proportion for vaccine minus population proportion for the control should just be 0 because they should be the same. Or you could think about it with an equals. So population proportion for V equals the population proportion for the control. And the alternative then is that the vaccine does work. So if it does work, let's think about this. If I subtract them, if it does work, this should be, the proportion for the vaccine should be smaller. If it's working, less people should get polio. And so if we have something smaller minus something bigger, we should actually get a negative number, right? Or it can be easier for me to think about it this way. If I want to just compare the two population proportions, I want the vaccine one to be less. And so that's an easier way sometimes for me to come up with that should be a less than sign. So now when I put it in to my applet, okay, group 1, there were 200,000 people that got the vaccine and 200,000 people that got the placebo. 56 people got polio in the vaccine group, 142 got polio in the placebo group. It will tell you your sample proportions. It might round differently than you did. Okay. Notice when it tries to do your segmented bar graphs, you can't even tell that there are like two different things on each one because the number of people that got polio were just so small that our sample proportions are just so small you can't even see it on the graph. And in fact, they're also small that when you subtract those proportions, the applet rounded, so it just said 0. So you do need to remember, we checked and it was 0.0004. In fact, it was negative 0.004. I apologize, I didn't write that down when I put it into my calculator. Okay, so the difference in proportions I had to write in here was negative 0.004 because it was so small the applet rounded it off. For my test of significance, the null will always just be equal to 0. Okay, but right here we said that this should be a less than for my alternative, so we put this less than right here. Okay, make sure you change that. It will tell you your mean and SD, again, it's rounding them both to 0 because we're dealing with such small proportions. But it'll tell you my standardized statistic, and my p-value is just basically 0, rounded that to 0 as well. And it will give you your confidence interval if you click that box. So my p-value is approximately 0. And if I wanted to interpret it, we'd say something like, if the vaccine has no effect, okay, if the null is true, then there is a 0%, or about, it's not exactly 0, just rounded, about a 0% chance that we would get such a big difference in our sample proportions. So that just does not seem plausible at all. Okay. So we could say something like, that is a small p-value. So the null is not plausible. And we'd say we have evidence for the alternative. Okay. Or in this case, evidence that the vaccine works. Now, what is your 95% confidence interval? It tells me that right here. So it's negative 0.0006 to negative 0.0003. And to interpret that, I could say something like, we are 95% confident that the decrease in polio rates is between. Now, it did say decrease, so I don't actually have to put in those negatives. So decrease means that we're saying the negatives. So we'll say between 0.0003 to 0.0006. Okay. So the polio took our proportions down by that much. Again, it doesn't seem like a lot, but for the people that got polio, it was really horrible. If you could reduce this by even a small amount, it was worthwhile. And the people that did get polio, even after the vaccine, didn't get as sick. And eventually with the vaccine, we were able to completely eradicate polio in America, which made it all worth it. Okay, one more example. Students at Cal Poly were randomly assigned to different treatments explaining a concept. Some of them watched video 1 and some of them watched video 2. They were then asked a question, and we want to know if one of the videos was better at teaching the concept. So video 1 or 2, that was our explanatory variable, and then whether they got it correct or incorrect was our response variable. So we're set up correctly. That's good. Let's state the appropriate null and alternative hypotheses for the study in words. Okay. So the null hypothesis would be that video 1 and video 2 have the same rates of correctness. And the alternative, okay, did it say if one of them was better? It didn't say which one I think is better. So we'll say video 1 and video 2 do not have the same proportion of correct. And those are population proportions. Let's write it in symbols as well, just to practice. So the proportion for the first one minus proportion for the second one would be equal to 0, would be our null. The alternative is that they are not equal to 0. We can't say whether it's greater than or less than because they didn't tell us which one they thought should be better. Are our validity conditions met to use a theory-based approach? Well, remember, we only look at our actual successes and failures, not the totals. And we need all of those to be at least 10. In this case, no. Because 5 is too small. The others are okay, but 5 is too small, and we need all of them to be at least 10. So we need all of them at least 10. So because our theory-based approach is too small, we have to use simulation. So we have to use the simulation. So we're going to pull up our two-proportion applet. Okay. And we put in our data just like we've been doing. Let me pull it up and put that in for you. Okay, I pulled up the applet. I put everything in. Double check that your totals match. Don't forget to click table. I did that just earlier today. I forgot to click it and I was wondering why my answers weren't right. Click show table here. I like to see that I put it in correctly. I can see the individual proportions for each group. It will show me the observed difference in the proportions. Okay. And I'll go to my show shuffle options and I need to shuffle 1,000 times. It's a pretty small sample size, so it doesn't take very long. And we need to count samples beyond what I got for my difference in proportions. So my difference in proportions is this negative 0.206. You can see that right here, this negative 0.206. Count. Okay. And my p-value is 0.3302. Now I do want to demonstrate the difference between the simulated and theory-based. So I am going to click on this overlay normal distribution so I can get my theory-based just for comparison. Also, you can click this 95% confidence interval, but again, this will be your theory-based confidence interval. So this is your theory-based. And let's see, and if we look at this count right here, this is my simulation. And this is my theory. So let's look at this. What was my simulated test statistic? It will not tell you on here your simulated test statistic. I feel like it should, but it doesn't. So let's figure out what that would actually be. Remember, it's your statistic minus the mean of null over the SD of null. So my statistic, what I actually got for my statistic is this negative 0.206 minus the mean, which it might not be exactly 0 because you're using a simulation, but we know theoretically it should be 0. So you are welcome to either put 0 or this 0.01. Either way, your answer is going to be close enough. And divide by the standard error of it, which according to our simulation is 0.16. Put this into your calculator and you should get negative 1.2875. This should usually be pretty close to your theory-based test statistic, but because it's a simulation, it'll be off a bit because the standard deviation isn't necessarily exactly the same as what we get with our theory-based approaches. Okay. What is the simulated p-value? It is 0.3324. Let's see, what is the theory-based test statistic? You just read it off here. It's just C equals negative 1.30. And the theory-based p-value is 0.1947. Notice, these are very different. So sometimes that happens when you have a small sample size. Your theory-based p-value and your simulated p-value can be very different. Okay. Now, which one should we use? We should use the simulation-based because our sample size was not big enough to use the theory-based approach. So we need to use the simulation-based p-value. And let's interpret that. So we can say something like, if, I would like to capitalize if because that's the big if. It's saying if. We're assuming if the null is true. So if the videos are the same, okay, same effectiveness, then there is a 0.33 chance that we would see such a big difference in our sample proportions. And what was the difference we saw? Of negative 0.206 or more extreme. Okay. That seemed like actually a pretty big difference in our proportions, but our sample size was so small. Okay, that is saying, yeah, that sample size is so small, you actually could see that big of a difference pretty easily just by chance. In fact, there's like a 33% chance that you would see such a big difference just by the chance of who you put in each group. Okay. And so what is your conclusion? We'd say something like, that is a big p-value, so the null is plausible. Okay. And then we can say something like, we don't have any evidence that one video was more effective than the other. So let's keep practicing now. What would we do if it asked you for your confidence intervals? So what is an approximate 2 standard deviation simulation based 95% confidence interval? Okay, this one you have to do by hand because it only gives you the theory-based confidence interval on the applet. So you have to do it by hand. You need your statistic plus or minus 2 times the standard error of your statistic. So our statistic is negative 0.206 plus or minus 2 times the standard error, which we just read as the standard deviation here on my output, 0.160. So we'll do negative 0.206 minus 2 times 0.16. Gives me negative 0.526 to 0.114. Let's see, what is our theory-based 95% interval? That's just our negative 0.507 to 0.095. Let's see, which interval is more appropriate here and interpret it? Well, we had a small sample size and our validity conditions were not met. So we need to use the simulation-based approach. So to interpret it, I have two different ways that we could interpret it. They all mean the exact same thing. I just want you to get used to different wordings. The first one, the most simple, is like we're 95% confident that the difference in the population proportions is between negative 0.507 to 0.095. Nope, sorry. We need to use our simulation-based ones. I just looked at the wrong numbers. Negative 0.526 to 0.114. This is truly like what it means when you boil it down, okay? But we can word it different ways, okay? So that's the simplest meaning, but we could say something like, we're 95% confident that the proportion correct with video 1 is, and I said larger here, so I'm still going to say video 1 was actually lower, so we'll say negative 0.526 to 0.114 larger than the proportion correct with video 2. So it didn't say the decrease like it did before, so I didn't have to change my signs. These are just the numbers I had, so that's how much higher video 1 is. Based on the confidence interval, is 0 a plausible value for the true difference in population proportions? Yes, because 0 is in the interval. So based on just the confidence interval, what could you say about the p-value? Okay. Because 0 is in the interval, the p-value must be bigger than 0.05. Okay. Anytime 0 is in the interval, 0 is plausible. That means it's a big p-value. Let's try that. 0 is plausible. So that's how you know it's a big p-value. Let's see. And for practice, what would happen to the width of the confidence interval if we used a 90% confidence level? So we know that if this was like 90%, then 95% has to be wider, right? So if we're going from 95% down to 90%, then it would have to be narrower. Okay. Sometimes she tells you to go from like 90% to 95 or from 95% down to 90%. So I like to kind of draw something like this, and then I can figure out what I should answer. What would happen to the width of the confidence interval if we used a larger sample size? So we know that larger sample sizes have smaller standard errors, and so larger sample sizes mean narrower confidence intervals. So higher confidence levels means wider confidence intervals, the way you become more confident to make your interval wider, and larger sample sizes mean narrower confidence intervals. We've been doing that for a while, practicing. It stays the same for all of our confidence intervals. That never changes. Okay. Well, what happens if we switch the order of the groups? So we're still back on the video example, but for now, let's say the professor that made video 2 insists that his video is better. Let's see if there's any evidence of that. So we think that video 2 is better than video 1. That's kind of what he thinks. Okay. Here's our data. Again, this is my explanatory variable up here. This is my response variable, so we're in the correct order to use the applet. Okay, let's figure out, so if I want to change the order, so if I write video 1 first minus video 2, let's figure out our null and alternative hypotheses. The null hypothesis will always just be that they're equal to 0. That's super easy. The alternative hypothesis, well, if I do video 1 first, it says we think video 2 is actually bigger. So if I do a small number minus a big number, that should actually be less than 0. Okay. And then we pull up the applet. This is all of the data that we've already had. So we had a negative 0.206 is our statistic. Okay. My p-value was 0.0481. You'll notice right here, because my alternative was a less than, I do have to change to count my samples for a less than. Okay. And I get this p-value here of 0.0481. And this is the confidence interval that I just found, the simulation-based confidence interval, since we said we need to use a simulation-based interval. Okay. But so that's what we did, the only difference being that this was a less than. But now let's see, what happens if we want to switch our order? So now we want to do video 2 minus video 1. Well, my null is still always in equals. But now we do video 2 first, and video 2 was supposed to be the bigger one, and video 1 is supposed to be smaller. So when I do a bigger number minus a smaller number, I should get something that's bigger than 0. So we're going to do a greater than. And let me show you on the applet. So we had everything into our applet already. The only thing you have to do is change this to a greater than. Okay. But also right here where it says success correct, and then you just click video 2 minus video 1. And it will change the groups for you. So your observed difference in proportions is now 0.206. Okay. You do have to click the greater than. Unfortunately, you also have to shuffle again. Okay. And when you shuffle again, you'll get slightly different results because it's a new simulation. Okay. So it'll give you your new p-value. Okay. Oh, but I need to change this. My statistic is no longer negative 0.206. My statistic is positive 0.206. Okay. So now there's my new p-value. Let's come back to this. Okay. So you can see your observed difference in proportions change from negative 0.206 to positive 0.206. We have to count samples greater than, and then we put in our positive 0.206, and we get a p-value. And to find my confidence interval, I do my new statistic, which is 0.206, plus or minus 2 times that standard error, which is the standard deviation right here. And so I get this confidence interval. So if we switch the order of the groups, what happens to each of these things? So the hypotheses, what did we have to change? We had to change the sign from a less than to a greater than. So we change from less than to greater than. What about the statistic, the observed difference in our proportions? We went from negative 0.206 to 0.206. So it stays the same, you only change the sign. So you only change from negative to positive, or vice versa if you started with a positive. Okay. Your standardized statistic, well, we didn't find it by hand, but if we just look at the theory-based approach, the only thing that's going to happen is you'll change from a negative to a positive. So only change from a negative to a positive. Okay. What about the p-value? Okay. The p-value, well, on your simulation, it stays about the same. Okay, for theory-based p-values, it's going to be exactly the same. For the theory-based, and close for the simulation. Okay. Your confidence interval, what happens to your confidence interval? It looks like those are the exact same numbers. We just switch from positives to negatives. And your conclusion, is your conclusion going to change? Either way, you have the same size of p-value, okay, although one is slightly less than 5% and one is slightly bigger. But really, as long as you have the same p-value, you get the exact same conclusion. So the conclusion will be the same because the p-values are the same. Okay, and it doesn't matter if we say that video 1 is less than video 2 or video 2 is greater than video 1. Either way, those mean the same thing.